Hello, I'm the moving Mr. Daycock, and today I'm going to be teaching you about implicit differentiation. So implicit differentiation is when you have a curve defined implicitly, like this. So this is an implicit curve, and it's implicit because there is no simple explicit function where we can write y equals something of x. Instead, each point is defined by whether or not it satisfies this equation. So you can test various points. You can go, does 0, 0 work? And 0, 0 does indeed work. If you put 0, 0 in, we get 0, and so on and so forth. You try lots and lots of different points. You can find that y equals to 0, x equals negative 1 works. You can find that you can plug in 1, 1 will work. If you plug in 1, 1, we'll get 2 and 2 on both sides, so 1, 1 satisfies this equation. If you plug in negative 2, 1, that also works because we're going to get on this side, we're going to get 1 plus 1. On this side, we're going to get 4 minus 2, and both sides equal 2 again. And that is how implicit functions work. It's just about checking whether or not all the sets of points satisfy the equation. Now, doing that, we are going to end up with this curve. And as you can see, this curve is not a function in the standard sense. It is not possible to plug in one value and get out a single value each time. There are a set of points, an area here, where if we plug in a value of x, we'll get out multiple values of y. And equally, there are lots of points where if we plug in a single value of y, we'll get multiple values of x. But nevertheless, even though this curve isn't defined in the simple way, it does still have a gradient. We can at any point go, ooh, what's the tangent here? What's that going to be? Or down here, what's the tangent down here going to be? We can ask ourselves these questions, and so there is still a gradient, and so we still want to be able to differentiate it. Now going back to this, so we want to be able to differentiate, find dy by dx when we have y cubed plus y squared equals x squared plus x. Well, that's what we want to be able to do. We want to be able to find dy by dx from that. Now, we could try differentiating with respect to y or with respect to x, but neither of those are going to be easy. But because we're looking for dy by dx, I'm going to differentiate with respect to x. So I apply d by dx on both sides and see what we get. So on the right hand side, pretty easy. This is all just in terms of x. If I differentiate it with respect to x, I'm just going to get 2x plus 1. Brilliant. On the left hand side though, things are a bit more complicated. Here I'm going to get d by dx of y cubed plus d by dx of y squared. Now if it was just y, that would be easy, because if it was just y, we would just get dy by dx. Because hopefully we can remember from the original idea that that is what d by dx of y means. It's just dy by dx. Or in fact, the other way around, what dy by dx means. And so from here, what we need to do is ask ourselves, how are we going to deal with this? What are we going to do to show that d by dx of y cubed is whatever it is? How are we going to work that out? And the answer is we're going to go to our friend the chain rule. We're dealing with d by dx of y cubed, but that is just very simply going to be d of y cubed by dy plus, no, not plus, multiply, because it's the chain rule, dy by dx. Now dy by dx, this part is fine, we like this. Dy by dx, we know what's going on here. And in fact, we know what's going on here. D of y cubed by dy, well, we're just taking y cubed and differentiating with respect to y. So that's just going to be 3y squared. We're literally just differentiating the y cubed with respect to y. So we get 3y squared, just like if I differentiated x cubed, I goes to 3x squared. That's all that's going on here. And then we've still got the dy by dx, which is what we like. We want that. That's the original thing that the question was asking for. So from here we get 3y squared dy by dx. And then for the second part, so that's this bit here, for the second part, d by dx of y squared, well, it's exactly the same thing. If we differentiate it with respect to y squared, we need dy squared by dy multiplied by dy by dx. But differentiating y squared with respect to y, well, that's just going to give us 2y. So it gives us 2y still multiplied by dy by dx. And that's equal to 2x plus 1. And so this here is our key function with these dy's by dx's in, but with our 3y squared plus 2y equals 2x plus 1. Okay, and now what we want though is we want dy by dx, so we want to rearrange to get dy by dx. So first of all I'm going to factor it out, so dy by dx multiplied by 3y squared plus 2y is going to be equal to 2x plus 1. All I did there was factor out the dy by dx from both terms. And then from there we're going to get dy by dx is equal to 2x plus 1 all over 3y squared plus 2y. And this here is an implicit formula for dy by dx. And it's implicit because, again, there's no explicit thing in terms of x or y. It's a mixture of x's and y's together. So we get dy by dx is equal to 2x plus 1 all over 3y squared plus 2y. Okay. So that was part A. We end up with dy by dx is equal to 2x plus 1 all over 3y squared plus 2y. Now, part B. Calculate when this curve is instantaneously vertical. So that means when it is the gradient, the tangent would look like that, where the tangent is just a simple straight line. Now, looking on this graph, you might be able to predict where that is, but you won't necessarily always have the graph, or the graph might not be as easy to read as this one. But so how do we answer this question? How do we work out where these points would be in a more general sense? As you might be able to see that they are here and here, so we're expecting the answers to be the point 0, 0 and the point -1, 0. But how can we prove that? How can we use the equation to do that? Well, it helps us if we think about what happens what it means when it's instantaneously horizontal. In this case, we're looking at dy by dx equals 0. So what does it mean for it to be instantaneously vertical? Well, it's kind of the other way around. So rather than dy by dx equals 0, we're looking for dx by dy equal to 0. So here, all we need to do is write down dx by dy equals 0, which means we're dealing with, because this is flipped, 3y squared plus 2y over 2x plus 1 equal to 0. Which means we're dealing with 3y squared plus 2y equals to 0 by multiplying by 2x plus 1. And remembering, of course, that this only works, this only makes sense if x does not equal -1/2. And now we just need to solve this. So it's going to work at the points when 3y squared plus 2y equals 0, which is going to give us the points 3y squared is equal to -2y. Well, in fact, what we don't talk about, we don't want to do that. We want to factorise. So we'll factorise out the y, and we get y lots of 3y plus 2 equals 0. And so we're looking for y is equal to either 0, or we get 3y plus 2 equals 0. And from here, we're going to rearrange, and we get y equals -2/3. So our two options are y equals 0, or y equals negative 2 over 3. Let's see if we can see those on the graph. And the answer is yes. The obvious ones were the 0, here and here, but perhaps slightly less obvious were the ones here and here, which are at negative 2/3 on the y-axis. So now we want to find out the x values of these. So where are we going to go to find the x values? It's very, very tempting to go back to this, but remember this is the gradient curve, not the equation of the curve itself. What we want to do is go all the way back to this original point. So we've got these two values of y equals 0 and y equals negative 2/3, and we want to re-put those into y cubed plus y squared is equal to x squared plus x. If I put in y equals 0, I'm going to get 0 is equal to x squared plus x, and that factorizes to x lots of x plus 1 equals 0, and that gives us x equals 0 or x equals negative 1. And so that gives us 2 points here. We get 0, 0 and 0. Oh, sorry, let's get that right. The x value is negative 1, so negative 1, 0, because these two are when y is 0 and x is these two values. So we get these 2 points. It's instantaneously vertical there. And let's consider this one now. A little bit more complicated. So we're going to get, plugging that in, we get negative 2/3 cubed plus negative 2/3 squared equals x squared plus x. And negative 2/3 cubed is going to give us negative 8 over 27 plus 4 over 9 equals x squared plus x. Let's add those fractions. So this is going to be 12 over 27, and so we get x squared plus x minus 4 over 27 equals 0. And at this point you would just use the quadratic formula, and you would find that your 2 points were going to be, let's in 0.131 negative 2/3 and minus 1.131 negative 2/3. And there we go. We have that, and we found all 4 points where the graph is instantaneously vertical. Okay, now that's not it, because it can get a little bit more complicated for the original differentiation. That's probably one of the more difficult ones for finding verticals that you'll find on a basic exam. But let's have a look at this. Find dy by dx when the natural log of y minus x squared y plus x cosine y equals negative 3. Now, this is a bit more difficult because we've got things being multiplied together here, and it ends up with a lovely looking curve like this. And if you're at all interested in this, I would recommend you use some kind of graphing program like Desmos or something along those lines, and just try out different values of this. Have everything else the same and just try out different values of that negative 3 and see what happens. It's quite an interesting curve with interesting properties. But for now, we're dealing with this. So find dy by dx when the natural log of y minus x squared y plus x cosine y equals negative 3. So we want dy by dx, so we're going to differentiate with respect to x on both sides. And that's going to give us d by dx of the natural log of y minus d by dx of x squared y plus d by dx of x cosine y, and that's going to equal 2. Well, if I differentiate minus 3 with respect to x, I end up with 0. That doesn't look like an x up there. Let's change that. Okay, now in each case we're just going to differentiate just as we were before, but thinking carefully about what's going on. So, from last time we were finding that if we were differentiating anything with respect to y, well then it was just the d lots of f of y, whatever our function of y was, differentiated with respect to y, multiplied by dy by dx. I.e., what that means is that you just differentiate the thing as though it was x. So we just imagine this was natural log of x, except that it's y, and then multiply by dy by dx at the end. So anytime there's a y there, we just differentiate it as though the y, it wasn't a y, and then just multiply dy by dx afterwards. Or whatever your independent and dependent variables are that you're using in regard to the differentiation. So in this case, the derivative of the natural log of y is 1 over y, and then because really we're differentiating with respect to x, we write dy by dx. So that is that, goes to that. Then here, this is slightly more difficult because it's a product. And so we're going to use the product rule. We're trying to do differentiate x squared y. And so I'm going to pick u equals x squared, v equals y. And that's going to give me the derivative of u dash, is going to be equal to 2x. And v dash is going to be equal to dy by dx, or 1 times dy by dx. And therefore, this thing is going to become minus, because we are still subtracting it, x squared dy by dx plus 2xy. And then lastly, we've got this one. It's another product. So we're differentiating x cosine y. So I'm going to pick u, wrote twice there, u equals x, v equals cosine y. So I get u dash equals 1 and v dash is equal to, well, derivative of cosine is negative sine, but it was sine of y, so we then multiply by dy by dx. And we're going to get, therefore, that this is going to be plus minus x sine y dy by dx plus 1 times by cosine y. And that, of course, all equals 0. And so the green one is this one here. Arguably not very fun, but ultimately it's just the product rule over and over again. If you have a product, use the product rule. If you have a product, use the product rule. Things being multiplied, product rule. And let's write this all out slightly neater. So we get 1 over y dy by dx minus x squared dy by dx plus 2xy minus x sine y dy by dx plus cosine y equals 0. And now we want dy by dx, so again we're just going to rearrange. We're going to move everything that isn't dy by dx, so these two things over to the other side, and we're going to get 1 over y dy by dx minus x squared dy by dx minus x sine y dy by dx equals, and we've shifted these across, so we get minus 2xy minus cosine y. And now what we want to do is we want to factor out this, because we're trying to look for dy by dx, so we're going to factor it out. So we're going to get dy by dx lots of 1 over y minus x squared minus x sine y is equal to negative 2xy minus cosine y. And therefore, dy by dx is equal to negative 2xy minus cosine y all over 1 over y minus x squared minus x sine y. And that's valid. You can leave it like that, but we don't, as mathematicians, we don't really like this, a fraction on the denominator of a fraction. So what I'm going to do is just multiply top and bottom of this by y. And in fact, there's a lot of negatives going on, so I'm going to multiply top and bottom by negative y to deal with those negatives as well. And that will give us that dy by dx is equal to 2xy squared plus y cosine y all over xy sine y plus x squared y minus 1. And that's a much nicer formula than the one above. And it's still incredibly implicit. As you notice, there's x's and y's everywhere, numerator, denominator, but ultimately that process was just one of product rule and our new implicit differentiation rule over and over again. So just remember, if you're dealing with some kind of product like this, apply the product rule. And if you're dealing with, always, if you're dealing with something like this, you want to differentiate, let's say, go tan y with respect to x, well, that's just going to become, the derivative of tan is x squared multiplied by dy by dx. That is the key rule of implicit differentiation there. If you're differentiating something in terms of y with respect to x, you're going to just differentiate it as though it was just differentiating with respect to y, and then multiply by dy by dx. Okay, thank you very much for watching, and I'll see you in the next video.